So welcome everybody. So in today's lecture we are going to just discuss little bit what are the various basic electrical quantities, and also we are going to I am going to give you a little bit insight into what a resistance is. Okay. So in electrical science we have four quantities, okay, measurable ones. One which is known as charge, the other one is current, voltage, and power. So charge, if you see what is the unit of a charge, it's coulomb. Okay, these things you have already done in your plus 2, so it's kind of just an revision. So charge is the unit is in SI is coulomb, right? And what is the charge of an electron? It is minus 1.6 into 10 to the power of minus 19 coulombs. So in 1 coulomb, so if I divide 1 divided by 1.6 into 10 to the power of minus 19, you get 6.25 into 10 to the power of 8 electrons. So that means 6.25 into 10 to the power of 18. These many electrons, when they come together, they represent 1 coulomb of charge. Okay, so that is the definition of a charge. So electron will have a negative charge, and proton will have a positive charge. Okay, so this is the first electrical quantity. The second one is current. Okay, so current is nothing but rate of change of electric charge, right? So it is given by dq by dt. So if you have a circuit, if you take a cross section anywhere in that circuit, the amount of charge and the rate at which the charge is passing through that cross section is known as current. Okay, so it is coulomb per second, or alternatively we call it as ampere. So 1 ampere is 1 coulomb per second, right? It indicates that the charges are moving from across that cross section wherever we have taken the reference. Okay, so they could be DC currents, they could be AC currents. DC currents is an unidirectional current, and which is then generally the sources are batteries, or AC currents are bidirectional currents, where the currents will be positive at an instant, at any other instance it could go negative, right? So it could oscillate between a positive and a negative magnitude. So like in household, whatever we have, the 220 volt AC supply and all, they give an AC currents. Okay, so this is the second quantity, current, which is again measurable. The third one is known as an voltage. Okay, it is the energy required to move a unit charge through an element. Okay, it is the work done to move a charge from unit charge from point A to point B. So between those 2 points there will be a potential. So that is known as voltage. Okay, and the unit is volt, right? It's an work done basically. And the last one is power, which we all know power is given by I into V, right? So I into V, essentially we are assuming that they are in phase, and we are talking about a DC currents as of now. When we take on AC supplies and AC currents, later on we will modify this definition. As of now we are speaking only about DC currents and DC voltages. So the power will be given into I into V, and the 1 volt into 1 ampere will give you 1 joule per second, which is also known as 1 watt. Okay, so these are the four basic electrical quantities. Okay, then moving on to what is a resistor. Okay, the resistor is the capacity of a material to restrict the flow of electric charge, or to impede the flow of electric charge. Okay, so the resistance is measured in ohms. So you have a voltage, whenever you apply a voltage out here, higher resistance means it will allow lesser current, and the relation between the voltage, current, and resistor is given by Ohm's law. Again, V is equal to IR, or I is equal to V by R, or R is equal to V by I, right? So this is how these three, this is the voltage, current, and resistance, and they are defined by the Ohm's law, the relation between these three. So this is one of the very basic equations, which we are using. Okay, is the voice breaking for all of you, or is it only for Webhow? Anybody?
I think it's
Sir,
only
it's
for him,
fine.
sir.
It's fine.
Sir, it's fine. Yeah.
Yes, sir.
Okay. So now if you see, when the current flows into the resistor, what happens? We know the power equation is given by V into I, right? So if I replace an I have given an voltage V, so I can be replaced by V by R, so it comes as V square R, or V can be again replaced with an I in terms of I and R, then it becomes I square R. So the power is now given by V square by R or I square R. What happens to this? Anybody? Where does this power go? Anybody?
So it is emitted out as heat.
Yeah, correct. So when we connect these kind of resistors, which is shown in the figure out here, so it will be heat. It will get heated up. These resistance, this energy. See, the law of conservation of energy says ki energy cannot be destroyed or created, right? So we are taking some current from the power source. So the power source is giving V into I. So that much power is being being consumed from the power source. So that power, if it is being consumed, it has to be accounted for somewhere in the circuit, right? So that gets converted as heat. Okay, so in these kind of resistors, I square R, so these resistors will get heated up, right? So you have immersion rod here, these kind of things also. Here also it takes an power supply volt of 220 volt and some current flows, and it gets heated up as I square R. Although you have conducting wires which connects various circuits, so even we have the wirings in our home, the resistance is very negligible, but still it's finite. So a certain amount of heat will be dissipated in these wires. So so always it is preferable that you use a good quality wire with good insulation. So basically the resistance should be as low as possible. That is the reason copper wires are mostly used, because they have very low resistance. Aluminum wires have got slightly higher resistance. So if you use copper wires, the amount of energy wasted will be negligible, and the heat generated will also be negligible, right? Similarly, you have incandescent lamps. So here also you will have I square R. So the resistance of these incandescent lamps will be defined by, see, the wattage will be given. If it's an 100 watt bulb, so and voltage also will be specified 220 volt. So P is given, V is given, so you can compute R, right? So it will be P V square by R. So you can compute the resistance. Now not that all IR, so again when a current flows, the power dissipated in this lamp will be I square R, but not everything gets converted as heat, and so because it is going to emit light also. So the total energy which will be consumed from the source will be I square R, in which a very small amount of energy will be converted into heat, and the majority will be converted into light. Okay. These days these are going out of fashion, because they consume lot of energy. They are not efficient. That means they don't convert the entire energy into light. A lot of energy gets converted into heat, which is not required. So now you have LEDs. So inside an LED bulb, if you see, there will be numerous LEDs, right? So these LEDs, they whatever again I square R will be the energy which will be consumed. In these LEDs, R is very large, but then it converts almost all the electrical energy consumed into light, and there is very negligible amount of heat produced. So they are highly efficient. Okay, so that is why these days we are for illumination we are switching to LEDs. Okay, so here again, but nevertheless the power consumed in all these will be I square R, right? So that I square R will be has to be somehow consumed, whether it is heat or light or a combination of that. Okay, so but law of conservation of energy, that rule needs to be satisfied. Okay. Now if you see, what in market you don't get any resistance of any value. Okay, the values of the resistances which are available are fixed. Okay, so in 1952 that IEC, International Electrotechnical Commission, decided that resistances should have a discrete value, so that when you are doing mass production, you can target on some specific values. So the designers know, okay, these are the specific value resistances which are available in the market. So this is a standardized. So in every decade you have 12 steps. Okay, so the resistance, like you can have a 10 ohm resistance, 12, 15 ohm, 18 ohm. You can't have a 16 ohm resistance. Generally you don't get. So you will have to use a potentiometer if you require a 16 ohm, or a series combination of these things. Okay, these are the standard 10, 12, 15, 18, 22. Similarly, you will have 100 ohms, 120 ohms, 150 ohms, 180 ohms, 820 ohms. And then you will have 1K, 1.2K, 1.5K, 1.8K, and 8.2K. Then you can have 1 mega ohm or 100K. Right. Similarly, 820K, 8.2 mega ohm, 82 mega ohm, so on and so forth. Is this aspect clear to all of you? Okay, why I am discussing this? If you are doing an actual circuit design someday, then you will have to take into consideration only these values of the resistors. Okay, you can't have any random value. Okay. How do we these are the resistors which you have, like they will be color coded. So how to find which resistor stands for what color code indicates what value of the resistor. So this is a standard table. So if you see the first band, okay, here is red. So if I go to red, it's 2, right? The second band, okay, it's a 4-band resistor. There are 4 bands. Now later on I will explain you what is a 5-band resistor. It's a 4-band resistor. That means there are 1, 2, 3, 4 band, right? So the first band stands for 2. The second band is an I can see here it's violet, so it is 7. And the third one is 10 to the power of whatever it is. Okay, so this is brown is 1, so 10 to the power of 1, that is 10. So it becomes into 10, so 27 into 10, that is 270 ohms. And the last one is the tolerance. Tolerance means there could be an plus minus 5% of error in this resistor. So the tolerance, if you see gold, is plus minus 5%. So that is how you compute the value of this resistor, seeing the color bands. Is this clear to all of you? So this is a standard chart which is available. Is it clear to all of you? Yeah. Okay. Similar, you could have only 3-band resistor also, in which this will not be given, the tolerance will not be given. Okay, but generally most of the resistors in the market starts with 4-band. Similarly, you could have an 5-band resistor also. In only the difference is, now here the 4th band will give you the exponential value. The rest of the things will give you the normal values, okay, in decimals. Like the first one out here, here if it is brown, black, okay. So brown is 1, black is 0, 0. So 1, 0, 0, and then it is orange. Orange is 3. So 1, 0, 0 into 10 to the power of 3. So 100 K ohms. Okay, and then you have this only. This is again brown. So this is more accurate resistor. So it has got plus minus 1% error. So you get. So looking at this table, this is how we can find out without actually measuring from using a voltmeter. Just by seeing the color band which is given on the resistor, we can say what is the value of the resistor. Is it clear to all of you? Okay. If you could respond, somebody either in the chat box or through your mic, it will be helpful, right? For me.
Yes, sir.
Okay. Let me just open up the chat box also. Right. Okay. So this is how. Now, if you see, this is 4-band, 5-band. There could be something known as an 6-band also. in the sixth, when I say 6 band, then the sixth one will be temperature coefficient. Okay. That generally we don't use much, but when in some circuits which requires very high accuracy, the fifth band will indicate that when the temperature changes, what is the deviation, that parts per million per Kelvin. So, with each degree change of temperature, how much is the value going to be changed, even that will be specified. But for any these are all very for specific where it's very critical, then we use these 6 band resistors. Generally till 4 band or 5 band will be good enough for us. Now it's not that a 1K resistor will be small and a 10K resistor will be big. Okay, so they all are generally of the same size, that we will understand because of the construction. So how is this resistors constructed is, see, you will have a core onto which there is an carbon strip, okay, in helical manner. So the thickness of that strip, the length of that strip, and the composition, all these things, they define the total net resistance. So that is why if you have if you want a low resistance, you will use a thicker film right here, that will be. So if you want a very high resistance, you will use a very thin film. Right, a small coil with a large number of turns. So that is how you realize. So externally they might all look the size wise they might look almost the same, but the values can differ right from few ohms to few mega ohms, because internally you have these kind of carbon films which are running, whose diameter, whose thickness and length can be varied to get the desired resistance. Okay, so that is there. So if you see another aspect of these things is the wattage of the resistors. This is the same resistor, okay, the same value. But if you see the first one which is shown here, it is of a very small size. It can dissipate 1/8 of a watt. Okay, so but if you are expecting in the circuit a larger current to be flown into the same resistor value, then you might have to use a higher wattage resistor. Okay, so you will have various. These are all the various resistors. As you see from 1/8, this is known as a quarter watt resistor, half watt resistor, 1 watt resistor, 2 watt resistor. Okay, the value of the resistor may be the same, but if you are expecting more current to flow into that resistor, it will generate more heat. So so accordingly these resistors will be bigger in size to dissipate that amount of current. If you are going to use small resistor and pump in say quarter watt resistor, and you are going to pump in a large amount of current, so then those resistors will get burnt. Okay, so you have to be not only the value of the resistor, you need to know what kind of current is expected to flow in those resistors. Accordingly you will have to choose the wattage. Okay, in earlier days in fan regulators also, to regulate the speed of the fan, we used to have these kind of ceramic resistors, where for a speed of 1, like we take just with each switching you will keep increasing the resistance in series. Okay, for 1 you will just take the output a small, for 1 you will take the maximum resistance in series, and then for as you keep increasing the speed, you will take a smaller amount of resistance in series. So here also you will find this was all very inefficient way of doing it. Nowadays we have electronic regulators. So these were in olden days used to have resistors connected in series, okay, to drop the voltage. Whereas again I square R heat used to be generated in these, so that is why these were so big in size. Okay, but there could be requirements where we require a specific value of resistors. In those cases we use something known as potentiometers. Okay, what potentiometers is like, you will have a resistor coil and you will have an an arm, moving arm in between, from where you can tap the resistance. Okay, so you can use these kind of. So in this particular example, if the total is say this from here to here, the entire coil, if it is say 1 kilo ohm, if you keep just exactly in between, you will get a 500 ohm and 500 ohm between these two terminals. If you keep it in the top between these two terminals, you will get 0 ohms, and between these two terminals you will get 1k. So you can adjust this value to any position and get the desired resistance. So these kind of potentiometers are also available in the market. These are all various kinds of potentiometers. Here also you need to take care of the wattage issue, not that you pick up any potentiometer and expect it to work satisfactorily in any circuit. You have to see the ratings of the potentiometer, how much current can they handle. So these things you have to be careful when in your designs. Okay. So these are some equations. We will derive these in the next class, but then just for tutorial purpose I am covering it out here, because we might have a tutorial before I start the next class. So if there are two resistances in parallel, right, now if you see the current, the same voltage which is being applied in these two resistors, so there will be one current which will flow here and one current which will flow here, right. So the net resistance which is offered by the combination of these two resistors will be much lesser, and more power will be drawn from the power supply. So the parallel resistor, the equation is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So the R equivalent will be lesser than R1 and R2. Okay, it will be lesser than both of these values. Okay, so similarly, if you have two resistors, this we will see the derivation later on. If you have two resistors which we connect in series, it is now both are going to oppose the flow of current, so they get added up. So the net effective resistance will be now higher. So because now you have to work harder to pass the current. Now two resistors are there, you have to work here. Here we have a parallel path, so it becomes easier for the current to flow. So here the net equivalent resistance is going to be R1 plus R2. Okay. These are some of the other important things which we should know, which is known as star and delta connections. Most of the generators, they are connected in star configuration. Okay, so this is an efficient way of generating electricity and transmitting electricity. So star means there are three coils which are connected in this manner, which is shown in the diagram, and this is known as the neutral. And you have red, blue, and yellow. These are the three. So this will discuss detail in the when we take up class on alternating currents. So this is just remember that this configuration is known as star, and this is known as delta. Okay, these what is the advantages of a star, delta, and things like that we will take up in the class when we study about AC circuits. But why I covered it here is when we talk about even resistances in circuits, we will encounter resistances which are connected like this in delta or star, and we should know how to convert this star connection into a delta and delta into a star. If we know that, the simplification of the circuit for analysis becomes easier. Okay. Whenever we encounter resistances which are connected like this, okay, there is a possibility that if we connect, if we replace it with an equivalent circuit like this, okay, solving the equation, the circuit will become easier. Okay, so that is the reason I have discussed this here. So we'll take up some practical numericals in the tutorials, but let me just cover the equations out here. So this is a delta connection. Now if I have to convert it into star, okay, this circuit I am going to read. Then what should be the value of R1? Okay, R1 will be given by RB into RC divided by RA plus RB plus RC. So if you see here RB, RC, okay, these are the two corresponding arms out here of delta. So this is the same node XX. So R1, RB, RC into RA plus RB. Similarly, if I take for Z, it will be it's R3, right? So if I have to find out R3, it will be RB and RA, product of RB, and then denominator it's all same, RAR. For R2, it will be RA into RC. Okay, so this is the way you convert a delta connection into a star. Okay. Similarly, if you have to convert a star into delta, okay, this is the formula. If you see RA, so you have R3 and R2, right, here, right, RA. So you have R1 R2 plus R2 R3 plus R3 R1. So this is R1. So this is R1. So you have an R1 R2 plus R2 R3 plus R3 R1 divided by R1. So this R1 comes in the denominator, because we are talking about the element which is going to get connected between Z and Y here. Okay, so this R1 comes in the denominator out here, right? Similarly, for RB, RB here, R2, that is the opposite arm out here, this R2 comes in the denominator. For RC, if you see RC, R3 comes in the denominator. Okay, this can be written in a different manner also in certain textbooks. RA will be written as R2 plus R3 plus like R1 gets cancelled here, here also R1 gets, plus R2 R3 by R1, right? So that also you can write it that RA is equal to R3 plus R2, okay, plus R3 R2 divided by R1. Okay, so you can remember that way also. So these are how to convert between star and delta connections. So this thing also will be required for your. So I'm actually putting a little bit of extra slides here so that these conversions, so that we progress the tutorials also. So these equations will help us in handling some problems which are slightly on the difficult side also. So these things I am putting it here. Okay, now let's see some of the applications of resistors. Okay, generally when we have, suppose I have a 9-volt system, I just want 4.5 volt. Okay, so to get 4.5 volt from 9 volt, I can use two resistances like this and get the desired voltage out here. If R1 and R2 are same, then I will get exactly half of it. So how do I get? This is the equation, right? The current which will flow out here will be V in divided by R2 plus R1, right? This is the V in divided by R, that will be the current. And what is the voltage across R2? That current into the value of this resistance, so R2. So this is the equation which we get to make a potential divider, right? That means to step down a voltage, we can use two resistances in series and tap the voltage out to basically to step down any given voltage. Okay, so one of the applications of the resistors is voltage, or it is known as voltage divider or potential divider, right? Here there is an example which is given out here. You have a 9 volt, you are applying 10k and you are taking a voltage out here. If you put a voltmeter, you will get a 4.5 volt. Okay, similarly you have a 12 volt here. It is now connected in the reverse direction. If you see here, so you have put 200 ohms and 800 ohms. So the voltage which will be available here will be 2.5 volt. It is not exactly the half, because these are not. So you will have to use this particular equation to compute the value of the voltage. It will be positive out here and negative out here. So okay. Now the question comes, okay, what should be these value of these resistors? Okay, so there is always an design issues there. So if you see here, if I use 1 ohms and 1 ohms, okay, still I will get 4.5 volt here. If I use 10k and 10k, still I will get 4.5 volt. So if I use 1 ohm and 1 ohm, you will find a large amount of current is going to flow in this circuit, right? Whereas I am not really interested in what the current, this is going to get wasted as IR square loss, right? This power, I am interested only at this terminal voltage, right? So I should use a large resistance. So why 10k? Suppose I use 1 mega ohm and 1 mega ohm here instead of 10k. Still I will get 4.5 volt, but why should I use 10k and 10k? Now if you see, it depends on the what kind of load you are going to connect. Suppose I use 10k and 10k out here, and I am going to use a 10 mega ohm load resistance. So this voltage, like 10 mega ohm, is actually going to come in parallel with this 10k, right? So that is not going to change the effective resistance here that much, right? So if it's not good, then this voltage will more or less remain 4.5 volt. But suppose I am going to use 100 ohms, okay, as a load resistor. So that 100 ohms and 10k, they will come in parallel. If they come in parallel, then the net effective resistance will be below 100 ohms, and then you will not get 4.5 volt, right? So in such cases, you will have to reduce these values of these two resistance, right? So if you are thinking of operating an 100 ohms load, then probably you will have to use 10 ohms and 10 ohms out here, right? So that while connecting the load or disconnecting the load, the voltage remains at 4.5 volts. So these are the design constraints you should remember, right? But using lesser resistance will consume power. So you clearly understand the voltage stability versus power consumption. These are the design trade-offs what you have. Is it understood?
Sir, can you please repeat?
Yeah, okay. See, I require an 4.5 volt output voltage. I suppose I have a 9 volt of cell, right? But my circuit requires only 4.5 volts. Okay, so I am going to use two resistors in series and take the tapping from in between to obtain this 4.5 volt voltage. Okay, so I can use a 10k, so I will get for 4.5 volt. Is this much aspect clear to you?
Yes, sir.
Yeah, okay. Now I can use, instead of 10k, I can use 1k, or I can use 1 ohm also, right? Still I will get 4.5 volt, right? Okay.
Yes, sir.
Yeah. So now what should be the value? So if I use lesser resistance, then a current will flow from this 9 volt through these two resistors. There will be circuit out here, right? So that will consume power. If it's a battery, then it will get consumed faster, and the battery will drain out, right? Or if it is a constant, and if it's an regulated power supply or something, commercial power supply, then these resistors will continuously keep getting heated up. So to save power, I have to use large resistance. Now 1 mega ohm and 1 mega ohm. Okay, suppose I use 1 mega ohm, still I will get 4.5. Now the problem using large resistance is, suppose I am using 1 mega ohm and 1 mega ohm, I am getting 4.5 volt, and my load resistor is say 100 mega ohms. So when I connect a load resistance of 100 mega ohms, so if you see the circuit, what happens is that 1 mega ohm and 100 mega ohm comes in parallel, right? But then that 1 mega ohm will become say 0.99 mega ohm. So it won't make any difference. But suppose I am connecting an 100 ohms load, so that 100 ohms will come in parallel with 1 mega ohm. So the effective resistance will be the load resistance and this resistance together. The net effective resistance will come below 100. Then it will not remain at 4.5 volts. So this voltage will drop, right? So you are not getting the desired voltage. So in such cases, the values of these resistance should be actually at least 1 order lower than the load resistance which you are connecting. Is it understood?
Yes, sir.
Okay. So these are some of the design aspects you should remember. So this will make things a little more clear. This is the potential divider. So if you see here, this voltage will be given by V1 into R2 divided by R1 plus R2. But when you connect and load resistance here, the net voltage will be I into R2. Now R2 will become parallel to RL, right? So it will be V1 R2 parallel to RL plus divided by R1 plus R2 parallel to RL, these two, right? Now if RL is much lower than R2, in that case the net resistance will become RL, and this will also become RL. So so what we had designed for the output voltage will not remain the same. okay, because the output voltage will be determined by the value of RL. Okay, so so that is why we have to be careful where we are going to use these kind of but these kind of potential dividers are used between two stages of an amplifier, because not in the final speaker output amplifier, but in the in between two amplifiers. If you want to give a we want to bring down the signal, we can use these kind of potentiometers, because the input impedance of the amplifiers are very high. So as long as RL is much higher than R2, there is no problem, these kind of potential dividers will work. Is it understood? Okay, whenever we make a potential divider, the RL value should be much higher than R2 for this design to work and for this equation to satisfy. Is it clear to all of you?
Yes, sir.
Okay. So that is why. Now these are some of the other applications what we have. Like you have a battery. Suppose you have a 9-volt battery. You have to switch on an LED. Right? What happens? The LEDs are generally, if you see, these are the specifications of LEDs which you will find. They typically require 1.8 volt. Maximum is 2.3 volt. And they require 20 milliamperes of current. So if you try to apply 9-volt battery directly to the LED, they will burn, right? So you have to add an resistor in series. Now to compute what is the value of the resistor, okay, you can use this equation. 9 volt is the battery voltage. You require 1.8 volt across the LED, 1.8 volt, and the current which should flow into the LED is 20 milliampere. So you divide, so you get 360. So this is the value of the resistance which needs to be connected in series with this LED. So is it clear how did I compute this value of this resistor? All of you?
Yes, sir.
Okay. So this is how I now 360 will generally be not be available. So the you will have to take 390, right? In this case, you can also take 470. So that will ensure that this LED is not fully glowing, but it will be slightly, but still it will be good enough. But that will prolong the life of the LED. So 470 ohms. You can put 390 also. But definitely no resistances below 390 is not recommended, otherwise this LED will blow off. Okay. So you can put 560, 680, but the brilliance of this will go lower. So it will not glow brightly, as brightly. So 360, 390 or 470 is an ideal resistance which needs to be connected in series in this way, right? Similarly, when we have microprocessors, most of the this is Arduino. So if you have to drive some LEDs based on an output from this microcontroller, so these provide a 5 volt supply. All right. So for since it's providing 5 volt, so you will have to put an LEDs again from 1.8 to 2.3 maximum. So you need to put a resistance in series. So the value can be computed again 5 minus 1.8 by 0.2. Okay, 0.02 is 20 milliampere. If you see, it is given in the specifications of an LED. So depending on what kind of LED you are using. So if you are going to use a 3.2 volt LED, so this 1.8 needs to be replaced by 3.2, and accordingly you need to compute the value of the resistances. Okay. So different LEDs, they will have different ratings. So this you need to get hold of this available in the net, or when you go into purchase an LEDs, the specifications will be given in the LED along with the manufacturing packing. These specifications will be given. So based on that, you need to select the required resistance which needs to be put in series. Okay. So with that we come to an end of this lecture. I have given a slight idea about resistors. So